Hello students, welcome back to yet another session. Today we are going to discuss degree of saturation and relative humidity. So these are the other psychometric properties, other two properties we are going to see in this session. So as we know, these are all the topics in unit number 4. Already we have seen properties of moist air, Gibbs-Dalton law, specific humidity and dew point temperature. In earlier 3 sessions we have seen these 3 topics, and now we are going to see degree of saturation and relative humidity. These are the two other psychometric properties we are going to see. In next session we will see the enthalpy, humid specific heat, and I am going to discuss wet bulb temperature separately. So wet bulb temperature itself is one more session, and then we will see the thermodynamic wet bulb temperature, then psychrometric chart, psychrometric of air conditioning processes, mixing of air streams. So these are the topics left out. We will be seeing in coming sessions. So first one is degree of saturation. So here I will show you one diagram. The figure again shows the same diagram, whatever diagram we have seen, TS diagram in earlier session, same diagram, and I will show you that the superheated thermodynamic state 1 of water vapor is in unsaturated moist air, representing the control volume V. So in that diagram, the water vapor exists at dry bulb temperature T of the mixer and partial pressure PV. So this is the diagram. You can see here the one is the superheated water vapor in unsaturated air state. So this is the point 1, and the point 2 is saturated water vapor in saturated air. So this is point 2, and we have other points as we discussed in earlier session. So this is the PV diagram, and sorry, TS diagram, and we have PS and PV. So this is PV curve and this is PS curve. So an imaginary isothermal process is assumed here, and the figure represents the change of state of water vapor in unsaturated air superheated at state 1. So this is the state 1 to saturated air at state 2. So from superheated state to saturated air, that forms the state 2 in this TS diagram at the same temperature. That is why it is known as isothermal process. It is isothermal imaginary process. So curve 1 to 2 shows addition of moisture leading to saturation. So from 1 to 2, it is we are adding the moisture to which leads to saturation. So PS is the saturation pressure. So this is PS is the saturation pressure at TS. So they consider now the more water vapor is added in this control volume V at a temperature T itself, the partial pressure PV. So partial pressure is the lower curve in the diagram, will go on increasing with addition of water vapor until it reaches the value PS corresponding to state 2 in figure 2. So that is the state 2, that is the isothermal state, and from 1 to 2 it forms isothermal state, and after which it cannot increase further as PS is the saturation pressure or maximum possible pressure of water at temperature T. So we cannot further increase the temperature or PS. So PS is the saturation pressure or maximum possible pressure of water at temperature T. The thermodynamic state of water vapor is now saturated at point 2. The air containing moisture in such a state is called saturated air. So here at point 2, the air containing moisture in this state, point 2 state, is called as saturated air, as we have seen in the diagram. So now in this state, the air is holding the maximum amount of water vapor. So now air is holding the maximum amount of water vapor, and that is in saturated state, and specific humidity omega s, and corresponding to the partial pressure Ps at temperature T of the mixer. So here this is the maximum amount of water vapor in this state. So that is nothing but the specific humidity. So that is nothing but specific humidity. We are going to denote that as omega s, and that is corresponding to partial pressure Ps at a temperature T of the mixer. So the maximum possible specific humidity, so possible specific humidity, that is the maximum at a temperature T, is given as, so that is specific humidity is nothing but maximum amount of water vapor. So omega s is equal to 0.622 into Ps by P minus Ps. So this is the simple equation with which you can calculate the specific humidity. And the rate of actual specific humidity omega to the specific humidity omega s. So here omega to omega s of saturated air temperature T is termed as the degree of saturation. So here this is the ratio of actual specific humidity omega to the specific humidity omega s is known as degree of saturation. It is denoted by the symbol nu, and thus nu equal to omega by omega s. So that is equal to Pv by Ps into 1 minus Ps by P divided by 1 minus Pv by P. So this is another relation with which we can calculate degree of saturation. So degree of saturation is a better measure of actual moisture carrying capacity of air at a given condition. So at given condition is nothing but the temperature and pressure. While the relative humidity compares moisture levels against saturation at the same temperature. So relative humidity gives the moisture levels at levels against saturation at the same temperature, and degree of saturation gives insight into how close the air to the actual saturation, factoring in specific humidity. So that is the importance of degree of saturation, because this gives the total insight into how close the air is to actual saturation and factoring in specific humidity. So that is the importance of degree of saturation. So degree of saturation is particularly useful in design of HVAC systems, cooling towers, and moisture sensitive processes. And in these areas, the degree of saturation is very much useful, and uh, we are going to calculate degree of saturation in our problems also. We will be discussing few problems on this. So next psychrometric property is relative humidity, and I have introduced the relative humidity earlier, and we will be discussing that in detail here. Relative humidity denoted by the symbol phi or RH. So in a few books you may find phi, or in few books you may find RH, is defined as the ratio of the mass of water vapor, that is MV. Mass of water vapor is denoted by MV in a certain volume of moist air at a given temperature of moist of water vapor MS in the same volume of saturated air at the same temperature. So this is the simple definition of relative humidity. It is defined as the ratio of mass of water vapor to the volume of moist air at given temperature of the mass of water vapor ms in the same volume of saturated air at the same temperature. So this is the definition of relative humidity. So referring to figure, the same figure that I have shown you earlier, the Vv and Vs are the specific volumes of water vapor in the actual moist air and saturated air respectively at a temperature T and in volume V at points 1 and 2, we see that, so that is pi equal to mv by ms. So this is the relative humidity definition, and PV V by RT and PVS by RT. So that becomes PV by PS. So also in terms of V also we can calculate it, and V by Vs. So that is VV by Vs. So that becomes Vs by Vv. So that is the simple way to calculate relative humidity in both ways, in terms of mass, in terms of volume. Any way we can calculate this. So using the perfect gas relationship between points 1 and 2, that is P1 V1 equal to P2 V2, so that is equal to PV equal to PS Vs. So PV VV equal to PS Vs. So therefore the pi equal to PV by PS equal to Vs by Vv. So in this, whatever parameters are given in the problem statement, using them we can easily find out relative humidity. So relative humidity turns out to be the ratio of partial pressures of water vapor in a certain unsaturated moist air at a given temperature T to the saturation pressure of water vapor, or it is nothing but the partial pressure of water vapor in saturated air. So at the same temperature T. So here the relative humidity turns out to be the ratio of partial pressures of water vapor and the partial pressure, the saturation pressure of water vapor. So partial pressure of water vapor to the saturation pressure of water vapor at the same temperature T. So that is the another way to define the relative humidity. So it is usually measured in percentage. So normally relative humidity is measured in percentage. When PV is equal to PS, so relative humidity will be unity. So that is 1, and the air is saturated, i.e., so that is the relative humidity is equal to 100 percentage. So normally we used to measure, or we used to represent relative humidity in terms of percentage. When PV equal to PS, the relative humidity is 100 percentage. While degree of saturation considers mass ratios, relative humidity is strictly pressure based. So here in degree of saturation, so in earlier property, it is mass based, and now relative humidity is strictly pressure based. So relative humidity is easier to measure using psychrometers and is commonly used in meteorology and comfort assessments. So it has many applications also, and it is used in many areas where psychrometers, and it is measured using psychrometers and commonly used in meteorology and comfort assessments. So that is HVAC systems. So in drying, air conditioning and combustion applications, degree of saturation may offer deeper insight into process limits. So in drying, air conditioning systems and combustion applications, degree of saturation is gives more information about the process limit, about the process itself. So derivations from the earlier equations, so it can be seen that the omega equal to that is 0.622 into PV by P minus PV. So omega S is equal to PS in terms of PS, degree of saturation, and now relative humidity is PV by PS, that is equal to omega by omega S into 1 minus PS by P divided by 1 minus PV by P. So this is how relative humidity and degree of saturation is measured. And now nu equal to the W by Ws equal to pi by 1 minus pi into Ps by P. So this is how we can calculate the nu, pi and omega s. So these three can be found out. And coming to our books, you can refer CP Arora. This is the best book and from this book only I have taken the entire material, and you can refer this book. This gives you complete information. You can refer Rajput, RS Kurmi also. Both are again good books. These are the books. So this is Kurmi you can refer. And the Ashe, this book is not giving much information, but you can refer for additional information. So Jones WP also, when we see next unit, it will be very handy textbook book. That is next Rai Dasat, that is also Principles of Refrigeration. This is also good book, but the entire content we can find in CP Aurora. And we have other NPTEL and online sources. And with this, we stop here, students, and again we will see the next topic in this unit in next session. Thank you. We'll meet again.